This is an AS Core Pure question on modelling with vectors. Part of the mains water system for a housing estate consists of water pipes buried beneath the ground surface. The water pipes are modelled as straight line segments. One pipe, W, is buried beneath a particular road. With respect to a fixed origin O, the road surface is modelled as a plane with equation 3x minus 5y minus 18z is equal to 7. And W passes through the points A, -1, -1, -3, and B, 1, 2, -3. The units are in meters. Part A. Use the model to calculate the acute angle between W and the road surface. So what we want to do is to find the angle between a line, that's the water pipe, W, and a plane, which is the road surface. And I'm going to use this formula to do it. So the sine of the angle is going to be the modulus of, so the reason I'm putting modulus is to ensure I get an acute angle, B dot N over the length of B times by the length of N, where B is the direction vector of the water pipe and N is a normal to the plane. And you're going to see that this form is probably the most straightforward form to use to find the angle, because it's really easy to get the normal to this plane from this equation. So let's start first of all by finding a direction vector for the water pipe, which I'm going to call B. So B is going to be AB. So to find that, I'll do 1, 2, minus 3. So this is point B minus point A, -1, -1, -3. And this will give me 1 minus -1, which is 2. 2 minus -1, which is 3, and -3 minus -3, which is 0. And in fact, any multiple of this vector will be fine as a direction vector for the water pipe. Now for the plane, which is written as 3x minus 5y minus 18z is equal to 7. If I can write that in this form, r dot n is equal to k, then here's my normal vector, and it's very easy to do that. So r is going to be x, y, z. N, that's just the coefficients of x, y, and z. 3 minus 5 minus 18 is going to equal to 7. So here's my normal vector here. So I can just write down that n is equal to 3 minus 5 minus 18. So now I can just put B and N into my formula. So let's just highlight those. Here's my B and here's my N. Okay, so the sine of the angle is equal to the modulus of, so we want to work out B dot N, so that'd be 2, 3, 0 dot 3, -5, -18 over, so we want the length of B. I'll do this calculation over the side because it's going to be like big massive thing down here. So length of B is going to be equal to the square root of 2 squared plus 3 squared plus 0 squared. So that gives me root 4 plus 9, so root 13. So I'll put root 13 here. And this is going to be times by the length of the normal. And so that's going to be the square root of 3 squared plus -5 squared plus -18 squared. And that gives a square root of 358, which I'll write down here. So I'll just finish this off by putting in the modulus symbol when I work out what the dot product to the top is. And actually I can now write down that theta is going to equal to, and it's going to be the sine inverse or the arc sine of this part here. Right, so let's start with the numerator here. So dot product 2 times by 3 plus 3 times by -5, so that's going to be 6 minus 15, which is going to give me -9 plus 0 times by -18, so that's -9. Then the bottom √13, √358. So because we're doing the modulus of this before we do the sine inverse or the arc sine, that negative is going to go. So let's see what we get for theta. So theta in degrees, 7.58088 and so on. So we want a sensible answer. I wouldn't round to the nearest degree, that's too much, but so we'll go for our normal 3 significant figures. So theta equals 7.58 degrees to 3 significant figures. A point C, -1, -2, 0, lies on the road. A section of water pipe needs to be connected from W to C. Part B, using a model, find to the nearest centimetre the shortest length of pipe needed to connect C to W. So what we need to do is to find the shortest distance between a point and a line, and I'm just going to run through the steps here that we need to do to find that. So we need to start by finding a vector equation for W. Then we need to find a vector from a general point on W using the vector equation for W to the point C. Then we want to find the specific point where the vector that we've just worked out here and the direction vector of W are perpendicular. And once we've done that, we can then find the length between C and this specific point on W that we've just found previously here. So we'll start by finding a vector equation for W. Now to find a vector equation of a line, we need a point that it passes through. So I've written down here the 2 points that W passes through. We were given that in the question. And we also need a direction vector of the line. And we worked this out previously in part A230. So this vector equation for W, we want to do a scalar times by its direction. So I'm just going to use the scalar lambda. So lambda 230 plus a point that it passes through. So I can pick either one of these two points that it passes through. I'm going to use this one, the -1, -1, -3. So I've done the first step. The second step is to find a vector from a general point on W to C. So let's first of all find a general point on W using this. And it's very easy to find a general point. You just basically lump together these two vectors into one. And if I do that, I will get 2 lambda minus 1, 3 lambda minus 1, and then just -3, like 0 lambda minus 3. So that's just -3. So there's my general point on W. So now we're ready to find a vector from this point here to C. So we can do that by working out the displacement between the 2 points. In other words, I can just do one vector minus the other. So here we go. This is a general point on W. Here's C. So the vector between the two will be 2 lambda minus 1 minus minus 1. So that just leaves 2 lambda. 3 lambda minus 1 minus -2. So that will be 3 lambda plus 1. And then -3, take away nothing, is just -3. So now we have our vector, which is from a general point on W to C. And what we want is we want this vector here to be perpendicular to our line W. Because remember, the shortest distance between a point and a line is a perpendicular line from the line to the point. So we want this to be perpendicular to W, and so we're going to do the dot product of this with the direction of W and make that equal to 0 and solve for lambda. Then we can find a specific point on the line which is going to give us this vector which is going to be perpendicular between that point and the other point that we're trying to find the distance, point C. So here's my dot product between this specific point or general point and the direction of W, which is this 230. So let's now work that out. So we'll get 2 lambda times by 2, so we've got 4 lambda, plus 3 lambda plus 1 times by 3. That gives 9 lambda plus 3, and then a negative 3 times by 0 is 0, and we're going to make this equal to 0. So from this we can solve for lambda. So we'll have 13 lambda is equal to negative 3. Therefore lambda is equal to negative 3 over 13. If I take this value of lambda and now substitute it into here, I can now get this specific point where I can get this perpendicular vector. So replacing lambda with negative 3 over 13, I will get 2 times by negative 3 over 13, which is going to give me negative 6 over 13. Then substituting lambda into here, so 3 times by negative 3 over 13 plus 1, which gives 4 over 13. And then the last one is just negative 3. So what we need to do now, finish it off, is to find the length of this vector. So the length of this, so it's just going to be Pythagoras. So the square root of negative 6 over 13 squared plus 4 over 13 squared plus negative 3 squared. Now this does give me an exact answer of 11 root 13 over 13. However, the question does say that we need to give the answer to the nearest centimetre. So let's see what we get as a decimal. So I get 3.05085 and so on. Okay, so my centimetres are going to be here. So that's rounding to 3 significant figures actually. So to the nearest centimetre it'll be 3.05 meters. I guess you could give your answer in centimeters as well. So you could give it as 305 centimeters. But yeah, that represents the shortest distance between this point C and the water pipe W.